Imagine pouring a bucket of water onto a concrete roof and watching it disappear through cracks you can barely see. Now imagine that same water slowly destroying steel, rotting structures, and causing millions of dollars in damage hidden beneath the surface. Every year, water infiltration costs the global construction industry tens of billions of dollars, yet most people never think about the thin protective layer standing between a building and disaster. That layer is called a waterproofing membrane, and the journey behind it is far more extraordinary than anyone expects. You see waterproofing membranes everywhere, but rarely notice them. They protect skyscrapers, bridges, tunnels, airports, dams, parking garages, and even the foundations beneath your feet. Some are thinner than a credit card, yet strong enough to survive decades of sunlight, freezing temperatures, and relentless storms. Think about this. A single membrane failure can threaten an entire structure, which means every roll leaving a factory carries enormous responsibility. But here's what nobody tells you. Waterproofing membranes don't begin inside a factory. Their story starts thousands of kilometers away in oil fields, limestone quarries, chemical plants, and mineral mines scattered across multiple continents. Before a single roll reaches a construction site, raw materials travel an astonishing global journey that rivals the supply chains of automobiles and electronics. And this is where our investigation begins. Most waterproofing membranes belong to one of two major families. The first uses modified bitumen, a material derived from crude oil. The second relies on advanced polymers, such as PVC, TPO, EPDM, and polyethylene. Although the finished products may look similar, their ingredients come from vastly different industrial worlds. What happens next surprised even experienced engineers. For modified bitumen membranes, the journey often begins in major petroleum-producing regions such as Saudi Arabia, the United States, Canada, and parts of the Middle East. Deep beneath the earth, drilling rigs extract crude oil from reservoirs formed over millions of years. After extraction, giant refineries separate crude into fuels, lubricants, and heavier fractions. One of those heavy fractions eventually becomes bitumen, the backbone of countless waterproofing systems. Inside a refinery, crude oil enters distillation towers that rise as high as a 20-story building. Temperatures exceed 350 degrees Celsius, or 662 degrees Fahrenheit, as operators separate valuable hydrocarbons. The lighter materials become gasoline and diesel. The heaviest residue remains at the bottom, dark, dense, and incredibly sticky. This residue forms the foundation of industrial-grade bitumen. Meanwhile, polymer-based membranes begin with natural gas and petroleum feedstocks transformed into plastic resins. Massive chemical complexes in countries such as the United States, China, South Korea, Germany, and Saudi Arabia crack hydrocarbons into molecules like ethylene and propylene. Engineers then rebuild those molecules into polymers with highly specialized properties. The result becomes the flexible backbone of modern waterproofing technology. But membranes need much more than bitumen or plastic. Manufacturers add finely ground limestone, calcium carbonate, silica, stabilizers, pigments, antioxidants, and fire-resistant additives. Some limestone quarries in Turkey, Egypt, and the United States process millions of tons of rock every year. Crushing plants reduce giant boulders into powders so fine they feel almost like flour between your fingers. Most people never think about this, but a waterproofing membrane may contain ingredients from 5 or more countries before production even starts. Polymer pellets arrive by rail. Mineral fillers travel by cargo ship. Specialty chemicals move inside sealed containers designed to protect purity levels above 99%. Every shipment must arrive at precisely the right time, or an entire production line can stop. Environmental challenges follow every stage of the supply chain. Oil extraction consumes energy. Quarrying reshapes landscapes. Ocean transport burns fuel across thousands of kilometers. In response, many manufacturers now incorporate recycled polymers and reclaimed industrial materials into selected membrane formulations. Some facilities have already reduced raw material waste by more than 30% compared to older production methods. Eventually, the ingredients converge at specialized manufacturing plants. Hundreds of tons of raw materials enter warehouses every week. Silos tower overhead like industrial skyscrapers. Workers, sensor, and automated systems verify every delivery before production begins. And hidden behind those warehouse doors, an intense transformation is about to turn powders, chemicals, and petroleum into one of construction's most important defenses against water. Because once the mixing begins, temperatures soar, giant rollers thunder across factory floors, and molten materials stretch into endless sheets moving faster than a highway traffic lane. The sights, sounds, and precision behind that process seem almost impossible until you witness them yourself. And in the next stage of this journey, we'll step directly onto production line, where waterproofing membranes are born. The moment production begins, the factory transforms into a world of heat, motion, and precision. Massive silos release carefully measured ingredients into automated feeding systems that never stop moving. Every kilogram matters because even a small variation can affect flexibility, strength, or weather resistance years later. Imagine standing beside a machine capable of producing enough waterproofing membrane in a single day to cover several football fields. For modified bitumen membranes, the process starts inside heated blending tanks. Operators pump bitumen into steel vessels and gradually raise temperatures to between 180 and 220 degrees Celsius, or 356 to 428 degrees Fahrenheit. The dark material churns continuously, while giant agitators rotate at roughly 30 to 60 revolutions per minute. The air smells faintly of hot asphalt, and the surface ripples like a black volcanic lake. Next comes one of the most important steps in the entire factory. Engineers introduce polymers such as AP, short for atactic polypropylene or SBS, known as styrene-butadiene-styrene. These materials dramatically improve flexibility and durability. Mixing can continue for 2 to 4 hours while temperatures remain stable and powerful motors blend the ingredients into a perfectly uniform compound. What emerges bears little resemblance to ordinary bitumen. Meanwhile, polymer membrane factories follow a different path. PVC, TPO, or polyethylene pellets enter high-capacity mixers, where additives, stabilizers, pigments, and UV-resistant compounds combine into a precise formulation. Temperatures typically reach 160 to 230 degrees Celsius, or 320 to 446 degrees Fahrenheit, depending on the material. As the mixture softens, it begins to resemble a dense, glowing industrial dough ready for shaping. Now comes the stage where raw material finally starts looking like a membrane. Powerful pumps force the molten compound through a spreading system that coats a moving reinforcement layer. Depending on the product, manufacturers use fiberglass mats, polyester fabrics, or composite reinforcements. The material flows across the surface like liquid lava, creating a perfectly controlled layer measured in millimeters. Think about this. Some production lines move at speeds between 10 and 60 meters per minute. That means every second matters. Laser-guided sensors constantly monitor thickness, while automated controls make adjustments faster than any human could react. If the layer becomes too thick or too thin, the system immediately corrects the flow rate. For reinforced membranes, another layer arrives from above. Massive rolls of polyester or fiberglass unwind continuously, while tension control systems keep every fiber perfectly aligned. The reinforcement becomes the skeleton of the membrane, giving it strength against tearing, stretching, and long-term structural movement. Without this hidden layer, many membranes would fail under real-world conditions. And this is where it gets truly extraordinary. The freshly formed sheet enters a series of calibration rollers applying pressures that can exceed 20 bar, or nearly 290 psi. These rollers compress the layers together while eliminating trapped air. The machines thunder across the factory floor, producing a deep mechanical roar that echoes through the building. Some products receive a protective surface treatment immediately afterward. Manufacturers may apply mineral granules, fine sand polyethylene films, or reflective coatings. Mineral-coated membranes create textured surfaces capable of resisting ultraviolet radiation for decades. Watching thousands of granules rain onto a moving sheet looks almost like an industrial sandstorm frozen in perfect order. The material now moves into one of the most critical phases: cooling. Cooling tunnels stretch dozens of meters across the factory. Powerful air systems gradually reduce temperatures from more than 200 degrees Celsius to near room temperature. Cool too quickly and internal stresses may form. cool too slowly and production efficiency drops dramatically. As the membrane exits the cooling section, automated inspection systems scan every square centimeter. Cameras search for bubbles, wrinkles, contamination, and thickness variations. Some systems inspect thousands of images every minute, while artificial intelligence compares each one against reference standards. What happens next surprised even veteran factory managers when the technology first arrived. Once approved, the membrane reaches a winding station. Giant shafts rotate with incredible precision as continuous sheets roll into tightly packed cylinders. Some rolls weigh more than 40 kilograms, while industrial versions can exceed 70 kilograms. Robotic handling systems lift, stack, and transport them without damaging even the outer edge. But here's what nobody tells you. Not every membrane survives the journey. Defective sections get removed instantly and recycled whenever possible. Workers constantly monitor quality indicators, temperatures, pressures, and production speeds because a single unnoticed flaw could eventually allow water to penetrate an entire building envelope. The pressure to achieve perfection never stops. By the end of the process, a material that began as crude oil, minerals, chemicals, and reinforcement fibers has transformed into a highly engineered barrier designed to survive decades of punishment. Yet the factory's toughest challenge still lies ahead. Because before a waterproofing membrane can protect a skyscraper, tunnel, or bridge, it must first survive a brutal series of tests that push it far beyond anything nature can deliver. Before a waterproofing membrane earns the right to leave the factory, it enters a world that feels more like a scientific laboratory than a manufacturing plant. Here, engineers deliberately stretch, tear, freeze, heat, and punish the material in ways most buildings will never experience. Imagine creating a product designed to survive 20, 30, or even 50 years outdoors. You cannot wait decades to see if it works, so you force decades of damage to happen in just a few weeks. The first line of defense begins with automated measurement systems. Laser scanners sweep across every roll as it moves through inspection stations. These instruments can detect thickness variations smaller than a human hair, often measuring tolerances within plus or minus 0.1 millimeters. If even a tiny section falls outside specification, the system immediately flags it for review. Most people never think about this, but a waterproofing membrane must remain flexible in winter and stable in extreme summer heat. To verify that performance, technicians place samples inside environmental chambers that simulate deserts, tropical climates, and Arctic conditions. Temperatures may drop to minus 40 degrees Celsius or minus 40 degrees Fahrenheit, then climb beyond 90 degrees Celsius or 194 degrees Fahrenheit. The material expands, contracts, and fights to maintain its integrity. Next comes tensile testing, one of the most important quality evaluations in the industry. Machines grip both ends of a membrane sample and pull with increasing force until it stretches or breaks. Powerful hydraulic systems record exactly how much stress the material can withstand. The machine groans, the sample tightens, and everyone watches the numbers climbing higher and higher. But waterproofing means nothing if water can find a path through the material. That is why manufacturers perform hydrostatic pressure tests. Samples face controlled water pressure that can reach several bars for extended periods. Sensors monitor every surface while technicians search for even the smallest leak. One microscopic defect can cause an automatic failure. And this is where it gets truly extraordinary. Some laboratories use accelerated weathering chambers equipped with powerful ultraviolet lamps. These systems bombard membranes with intense UV radiation 24 hours a day. In a matter of months, engineers can simulate years of sunlight exposure. What happens next surprised even experienced researchers when early generations of membranes fail far sooner than expected. Modern factories increasingly rely on artificial intelligence to catch defects invisible to the human eye. High-speed vision systems inspect thousands of square meters every hour. AI algorithms compare surface patterns against enormous databases of known defects. Tiny bubbles, contamination particles, wrinkles, and coating inconsistencies trigger immediate alerts before products reach packaging. Yet despite all this technology, there are moments when human experience still beats the machines. Veteran inspectors often run their hands across freshly produced membranes, searching for subtle irregularities. They can sometimes detect texture changes that sensors overlook. Decades of experience create a level of intuition that remains difficult to automate completely. Factories also perform adhesion testing to ensure layers remain bonded throughout the product's life. Specialized equipment pulls reinforcement fabrics away from membrane layers, while sensors record separation forces. Engineers study every result because poor bonding can eventually allow moisture to penetrate beneath the surface. The test may destroy the sample, but it protects future buildings. Fire performance testing adds another level of scrutiny. Depending on the application, membranes may need to comply with international standards such as ASTM, YEN ISO, or FM approval requirements. Engineers expose samples to control flames, radiant heat, and ignition sources. The goal is not simply to survive fire, but to slow its spread and improve overall building safety. Think about this. A large manufacturer may test hundreds of samples every day while rejecting 1 to 3% production before shipment. That might sound wasteful, but those rejected products prevent future failures that could cost millions of dollars in repairs. Quality control does not exist to protect the factory. It exists to protect the structures relying on the product. Once testing ends, approved rolls receive identification codes that allow complete traceability. Manufacturers can often track a finished roll back to specific production dates, raw material batches, machine settings, and inspection records. Every roll carries a hidden history. If questions arise years later, investigators can follow the trail all the way back to the factory floor. By now, the membrane has survived crushing pressure, freezing temperatures, ultraviolet radiation, stretching forces, and relentless inspection. It stands ready to protect structures around the world. But the scale of this industry is far larger than most people imagine, because behind every roll lies a global network worth billions of dollars, employing hundreds of thousands of people, and shaping the future of construction itself. Now step back from the factory floor and look at the bigger picture. The waterproofing membrane industry has grown into a global giant serving nearly every major construction project on Earth. Analysts estimate the worldwide market value exceeds $35 billion and continues to expand as cities build upward, outward, and deeper underground. Most people never realize that one of the construction industry's most important products remains almost completely invisible after installation. Every year, manufacturers produce billions of square meters of waterproofing materials. If you connected enough membrane rolls end to end, they could stretch across continents. Imagine covering entire cities beneath a protective shield designed to stop one of nature's most persistent forces. Water never stops searching for weaknesses, and this industry never stops developing new defenses. China currently represents the largest share of global production, driven by enormous infrastructure and housing projects. The United States follows as one of the world's largest consumers and innovators. India continues expanding rapidly as urban development accelerates. Germany remains a leader in advanced manufacturing technology, while Turkey plays a major role in supplying regional and international markets. Together, these countries account for a significant portion of global waterproofing membrane output. Think about this. Hundreds of thousands of workers contribute directly or indirectly to the waterproofing supply chain. Geologists locate mineral resources. Refinery operators process petroleum feedstocks. Chemical engineers develop polymer formulations. Factory technicians oversee production, while construction crews install finished products in every climate imaginable. A single membrane roll represents a combined effort of countless specialists. The history of waterproofing stretches back thousands of years. Ancient civilizations used natural bitumen to seal boats, reservoirs, and structures long before modern chemistry existed. Archaeologists have discovered evidence of waterproofing materials in Mesopotamia dating back several millennia. What began as simple natural coatings eventually evolved into today's sophisticated engineered membranes capable of surviving decades of exposure. Over the last 50 years, the industry has transformed dramatically. Early membranes often suffered from cracking, UV degradation, and limited service life. Modern materials incorporate advanced polymers, reinforcement fabrics, fire-resistant additives, and sophisticated manufacturing controls. Some premium systems now remain functional for 30 years or more under proper installation and maintenance conditions. And this is where it gets truly extraordinary. Researchers are developing next-generation membranes with self-healing properties, improved recyclability, and enhanced environmental performance. Some experimental materials can automatically seal tiny punctures before leaks develop. Others use advanced formulations designed to reduce heat absorption and improve building energy efficiency. The future of waterproofing may be smarter than anyone imagined. Did you know that a waterproofing failure hidden beneath a roof or foundation can remain undetected for months before visible damage appears? By the time water stains become obvious, moisture may have already traveled through insulation, concrete, steel, and structural components. What seems like a small leak can become an enormous engineering challenge. Did you know that ultraviolet radiation from sunlight ranks among the biggest long-term threats to exposed waterproofing materials? Day after day, year after year, UV energy attacks surfaces at the molecular level. That is why modern formulations contain specialized stabilizers capable of dramatically extending service life in harsh environments. And here's another surprising fact. Some of the most demanding waterproofing applications exist below ground rather than above it. Deep tunnels, subway systems, underground parking structures, and foundation walls face constant hydrostatic pressure from surrounding soil and groundwater. Invisible beneath cities, waterproofing membranes quietly perform one of the toughest jobs in modern construction. From oil fields and limestone quarries to chemical plants, laboratories, and high-speed production lines, we followed an incredible journey hidden beneath the surface of modern construction. What began as raw materials extracted from the earth transformed through heat, chemistry, engineering, automation, and relentless testing. Every stage demanded precision because failure was never an option. And yet, when installation is complete, the membrane disappears from sight, quietly protecting the world around us. The next time you walk across a rooftop, drive through a tunnel, enter a parking garage, or stand inside a skyscraper during a heavy storm, remember the hidden technology working beneath your feet and above your head. Most people will never see it. Most people will never think about it. But without waterproofing membranes, many of the structures we depend on every day would face a constant battle against water. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.